Have you ever really thought about the phone in your hands? I mean, it's basically a rock that we zapped with lightning and taught how to think. It really does feel like magic. But it all starts with an idea so simple it's kind of mind-blowing. A switch. Just on or off. So let's dive in and see how we get from that tiny little switch all the way up to a supercomputer. And that really is the heart of the mystery, isn't it? How do we take our complicated, messy, and let's face it, often chaotic world and translate it into the perfectly rigid, logical language that a machine gets? That is the big question we're going to unpack right now. It's really a story about translation. So to start, we really have to get our heads around the two basic ways information can exist. And that brings us to the two languages at the heart of, well, pretty much all modern electronics: analog and digital. And here's the difference in a nutshell. On one hand, you've got the analog world. It's smooth, it's continuous. Think about a dimmer switch for a light or the grooves in a vinyl record. There are literally infinite possible values between the top and the bottom. But the digital world, totally different. It's all about precise separate steps. It's either a 0 or it's a 1. It's on or it's off. There is absolutely nothing in between. So, why did digital take over everything? Well, it comes down to these huge advantages. Digital info is perfectly repeatable, which makes it super accurate. It's way more resistant to electrical noise or static because the system only has to figure out, is that a high voltage or a low voltage? Small fluctuations just don't matter. And maybe most importantly, it's incredibly easy to store, and you can tell it what to do with software. That combination of reliability and flexibility is what kicked off the entire digital revolution. Okay, so we've got the idea of zeros and ones down, but how does a machine actually, see them? Well, the answer is in the language of electricity itself. And this isn't some abstract theory. It's incredibly physical. Inside your computer, a 1 is simply a high voltage. Let's say it's around 5 volts. And a 0 is just a low voltage, something close to 0. That's it. By sending these quick pulses of high and low voltage, the machine is literally speaking in binary. Now, in a perfect textbook world, switching from that low 0 to a high 1 would be instantaneous. You'd get this perfect, clean square wave. An instant jump up and an instant drop down. But, of course, reality is a little messier. Because of the actual physics of the circuits, it takes a tiny amount of time for the voltage to climb from low to high. We call that the rise time. And it takes time to go from high back to low, and that's the fall time. This tiny little delay is one of the fundamental speed limits that engineers are constantly fighting to overcome. So we have our electrical letters, high and low, but letters aren't enough. We need a way to form words to make decisions. And this is where logic gates come in. They are, quite literally, the alphabet of all computation. A logic gate is just a tiny, incredibly simple decision maker. It takes in one or more of those binary inputs, those high and low voltages, and it spits out a single output based on a really simple rule. So, for example, an AND gate will only output a 1 if both of its inputs are also 1. It's that basic. And this is where it gets really cool. Once you have these simple decision makers, you can start combining them in clever ways to do more complex stuff. You can build circuits that do basic math, like adding or subtracting binary numbers. We're literally building intelligence from these simplest possible parts. The real power here is all about scale. Once you can add and subtract, you can start building all sorts of incredibly sophisticated functions. And the thing to remember is, all of these advanced functions, at their very core, are just really, really clever combinations of those basic and, or, and not gates. So let's take multiplexing. It's basically a data traffic controller. And honestly, the railroad switch analogy is perfect. Imagine you have information coming down lots of different tracks, and the multiplexer acts like the switch operator, guiding just one train of data onto the main line at a time. And that's exactly what you're looking at here. You have all these input lines coming into the multiplexer, or MUX for short, and it uses another set of inputs called select lines to decide which one of those inputs gets to go through to the single output. This is absolutely essential for managing the flow of data inside a complex chip. Okay, so we can make decisions, but what about memory? What happens if you arrange these gates in a special loop so they can actually remember a value? Well, that's the basis of storage. These circuits, called flip-flops, can hold on to a 1 or a 0 even after you take the input away. You chain a bunch of these together, and you get registers. the absolute fundamental building blocks of all computer memory. And there's another huge piece of the puzzle: counting. By arranging gates in yet another clever way, you can create a circuit that actually counts the electrical pulses it gets. This is fundamental to everything from the timer on your microwave to the internal clock that dictates how fast your computer's processor can run. So we've got decision-making, we have math, data routing, memory, and timing. But how on earth do we cram all of that into the tiny little devices we use every single day? Well, that brings us to the modern miracle of integration. Just take a look at this. The scale is mind-blowing. We started out with small-scale integration, or SSI, where you had less than 10 gates on a single chip. Today, we're at ultra-large-scale integration, ULSI, cramming millions, sometimes billions, of these tiny little logic gates into a space smaller than your fingernail. The growth has been nothing short of explosive. And this is the result of all that, the microprocessor. It's the grand finale, the culmination of everything we've talked about. It combines logic gates to create math units, registers for super-fast storage, and control circuits that act like the conductor of an orchestra for the whole chip. You've got the arithmetic logic unit, or ALU, where all the math happens. You have the registers for temporary storage, and you have the control unit that directs the whole show. At its very heart, the microprocessor is an engine running a simple but relentless cycle. It fetches an instruction from memory. It decodes that instruction to figure out what to do, and then it executes it. And it does this millions, sometimes billions of times every single second. It is, without a doubt, the brain of every modern computer. So the next time you look at your phone or your watch or your laptop, just remember what's really going on inside. It's billions of tiny, simple switches, all working together through basic rules of logic to create the incredibly complex digital world we all live in. It all comes back to just on and off, which leaves us with one final thought.